A nanostructure is an object that have at least one dimension in the range of 1 to 100 nanometers. In describing nanostructures, are categorized as zero-dimensional nanostructures. Nanotubes and nanowires have a characteristic diameter between 1 and 100 nanometers and a length that could be much greater than that. These structures are categorized as one-dimensional nanostructures. Nanocomposite surfaces or thin films have a thickness between 1 and 100 nanometer, while the other two dimensions are much greater. These structures are categorized as two-dimensional complex materials. Finally, bulk materials with all dimensions above 100 nanometer but that contain zero dimension or one dimension and or two-dimensional nanostructures are termed three-dimensional nanostructures. We will describe each of these nanostructures in more details in the next sessions. We will start now with defining the zero-dimensional nanostructure, which include basically the nanoparticles and the quantum dots. Nanoparticles are defined as small objects that are sized between 1 and 100 nanometers and that behave as a whole unit with respect to its transport properties. Nanoparticles are size dependent, namely, the properties of the materials change as their size approaches the nanoscale and as the percentage of the atoms at the surface of the material becomes significant. The interesting and the unexpected properties of the nanoparticles are therefore significantly due to the large surface area of the material, which dominates the contributions made by the small bulk of the material. For the sake of comparison, bulk materials, mainly particles larger than 1 micrometer, contain insignificant percentage of atoms at the surface in relation to the number of atoms in the bulk of the same material. And therefore, they don't behave or exhibit size-dependent changes in their physical properties. Nanoparticles often possess unexpected optical properties as they are small enough to confine their electrons and produce quantum effects. The size-dependent color of the nanoparticles was utilized, though without any intention, by artists as far as the 9th century for generating a glittering effects on the surface of pots or colors in stained glass. The unique physical properties of the nanoparticles allow much higher absorption of solar radiation in photovoltaic cells that are composed of nanoparticles than in thin films of continuous sheets, even that is composed from the same material. Other size-dependent properties change include quantum confinement in semiconductor particles, surface plasmon resonance in some metal nanoparticles, and chemical reactivity that are utilized for image formation in photography field. Now, from the zero-dimensional nanostructures, we will move to one-dimensional structures, which include, among the rest, nanowires, quantum wires, nanorods, and nanotubes. A nanowire is a nanostructure with a diameter of the order of nanometer. At these scales, quantum mechanical effects are important, and therefore they are coined the term quantum wires. Many different types of nanowires exist. These include, of course, metallic nanowires, semiconducting nanowires, and insulating nanowires. More details about each of these nanowires could be seen on the slide, and we will explain about these in the next lectures. On the other hand, molecular nanowires are composed of repeating molecular units, either organic, for example DNA, or inorganic material. New forms of nanowires include core shell superlattices nanowires, as seen in the bottom figure in the slide. Nanowires have two quantum confined directions while still leaving one unconfined direction for electrical conduction. Basically, this feature allows the nanowire to be used in applications where electrical conduction is required, and because of their unique density of electron states, nanowires in the limit of small diameters are expected to exhibit significantly different optical, electrical, and magnetic properties from their bulk three-dimensional crystalline counterparts. We will move right now to the carbon nanotubes. Carbon nanotubes are a long, hollow structure with the walls formed by one atom thick sheet of carbon, which we call usually, in the scientific literature, graphene. These sheets are rolled at specific and discrete chiral angles, and the combination of the rolling angle and the radius decides the nanotube properties. Individual nanotubes naturally align themselves into ropes held together by the so-called van der Waals forces, or more specifically, pi stacking. Usually the end of the carbon nanotube ends with half buckyball-like carbon structure. Carbon nanotubes have unusual properties which are valuable for the nanotechnology, electronics, optics, and other fields of materials, science, and technology. In particular, owing to their extraordinary thermal conductivity and mechanical and electrical properties, carbon nanotubes find applications as additives to various structural materials. For instance, nanotubes form a tiny portion of the material in some of their carbon fiber, baseball bats, golf clubs, or car parts. An inorganic nanotube is often composed of metal oxides. Inorganic nanotubes show various advantages such as easy synthetic access and high crystallinity, good uniformity and dispersion, predefined electrical conductivity, good adhesion to a number of polymers, and high impact resistance. These materials are therefore promising candidates as filters for polymer composites with enhanced thermal, mechanical, and electrical properties. Inorganic nanotubes are heavier than the carbon nanotube, which we have explained in the last slide, and therefore they don't have a strongness under tensile stress, but they are particularly strong under compression, thus leading to potential applications in impact-resistant applications such as bull roof visits. Two representative examples of inorganic nanotubes include, as could be seen on the slide, boron nitride nanotubes. This case, for example, or this material, have a high resistance to oxidation suited for high temperature. It has also Young modulus of 1.22 terapascal. It's also behaved as a semiconducting material, and of course the electronic properties of this material are predictable. And on the other hand, I would represent on the same slide an example on the silicon carbon nanotubes, which have also high resistance to oxidation, and it's quite suitable for harsh environments and can be functionalized with organic monomer